Hello and welcome to presentation 5 of 7 for Electrical Principles and Technology, the grade 7 science curriculum. Engineers and designers of electrical circuits use symbols to identify components and connections. A drawing made with these symbols is called a schematic or a schematic diagram. These are some basic electrical circuit symbols. I would recommend you look them up on the internet. Do a Google search because those are kind of terrible. All circuit diagrams have 4 basic parts. They have an energy source, which provides energy and a supply of electrons to the circuit, conductors, which provide a path for the current, a switching mechanism, which controls the current flow, turning it off and on, or directing it to different parts of the circuit. Loads convert electrical energy into other forms of energy. There are 2 types of circuits. One is a series circuit and the other is a parallel circuit. Series circuits only provide one path for the current to flow, whereas parallel circuits provide multiple pathways. House wiring uses parallel circuits. Microcircuits or integrated circuits. Transistors are used with 3 layers of specially treated silicone, with the middle layer receiving a small voltage, allowing it to control the voltage in the outer layers, allowing these to act as switches. Microcircuits are made up of transistors and resistors and are built on an extremely small scale. Integrated circuits put all of the components of a circuit onto one chip, reducing the size of the circuit substantially. Hans Christian Ørsted found that a current could create a magnetic field around a wire. Deflection of a compass needle using electrical current showed that there was a relationship between electricity and magnetism. By discovering electromagnetic induction in 1831, Michael Faraday was able to construct the first motor. While moving a conducting wire through a magnetic field, moving it back and forth through the field, Faraday created the first electricity-producing generator, which could generate electrical current. By coiling copper wire around an iron metal core with a strong electromagnet can be made. When attached to an electrical source, it will produce a strong magnetic field. To keep this electromagnet spinning with a magnetic field, the direction of the current is traveling through the coil must be switched. This is accomplished by a gap which allows the polarity of the electromagnet to change just before it aligns with the permanent magnet. Many electrical motors use a commutator, which is a split ring that breaks the flow of electricity for a moment and then reverses the flow in the coil. When the contact is broken, so is the magnetic field. The brushes are contact points with the commutator and are used to reverse the flow of electricity through the magnetic field. The armature, or the rotating shaft with the coil wrapped around it, continues to spin because of momentum, allowing the brushes to come in contact once again with the commutator. So, an analogy that you can think of. Turning a steering wheel is similar to the turning of the armature in a motor. At some point, you have to release the wheel and start again. This is what the commutator allows the armature to do. Direct and alternating current. Some motors run on direct current or DC. This is direct because the electricity flows in only one direction. Alternating current or AC flows back and forth about 60 times a second. Generating DC and AC. A DC generator is much the same as a DC motor. The spinning armature produces the electricity. If electricity is passed through a DC generator, it will spin like a motor. The central axle of an AC motor has a loop of wire attached to 2 split rings. The current is switched as the loops move up and down alternatively through the magnetic field. The slip rings conduct the alternating current to the circuit through the brushes. The brush and ring assembly allows the whole loop to spin freely. In large AC generators, many loops of wire are wrapped around an iron core. Transformers are used to change the amount of voltage with hardly any energy loss. Voltage change is necessary because the most efficient way to transmit current over long distances is at high voltage, and then reduced when it reaches its destination, where it will be used. A step-up transformer increases voltage. The step-up transformer is used from the electrical generating station to the transmission lines. A step-down transformer reduces voltage. The step-down transformer is used from the transmission lines to the consumer's homes. Electrical power. Power is the rate at which a device converts energy. The unit of power is the watt, which is equal to 1 joule per second. For an electrical device, the power is the current multiplied by the voltage. Power is found in watts, current is measured in amperes, and voltage is measured in volts. So power is equal to current times voltage. Current is equal to power divided by voltage, and voltage is equal to power divided by current. Energy is equal to energy in joules. Power is measured in watts, which is a joule per second, and time is measured in seconds when we're talking about electrical power. So E is equal to P times T is your formula to remember. Energy. The power rating of a device can be used to determine the amount of energy the device uses. Multiply the power rating by the time the device is operating. Kilowatt hours are used as a unit for energy. The energy calculation is the same, except that hours are submitted for seconds and kilowatt hours are submitted for watts. Electricity meters measure the energy used in kilowatt hours, then bills you for every kilowatt hour used. So here's an example of an electric meter.